Like the wiper blades in a car, you know that you can set it to operate at different times, right? You can make it go faster or slower. Or even the traffic signal lights, that also has a timing, of course, connected to it. Or, as I'll explain later, a sawtooth generator, an electronic device that produces some kind of waves that also has a timing. Really, any timing circuit is actually an RC circuit. It's actually a resistance of a very high value connected with a capacitor, and both are in series with each other. So what's going to happen is you have a capacitor connected to a high resistance put in series with a battery, and the capacitance is going to get charged through the high resistance. Okay, so it's called an RC circuit, and there's also a lab coming up on the RC circuit. That's the circuit. You have the battery, you have the resistance and the capacitance in series. Let's say that the resistance is R ohms, the capacitance is C farads, and S is a switch. E is the maximum potential difference of the battery. We call it the EMF. And when the switch is, when it's switched on, you know that what's going to happen is electrons are going to flow from the negative of that battery. So it'll go from the negative and it'll go to the capacitor, right? From the negative of the battery to the capacitor. So the upper plate of the capacitor will get negatively charged while the bottom plate becomes positively charged. Now, does that set up a potential opposite to the battery, or is it going to be the same kind of potential as the battery? Yeah, up to what point will the capacitor accumulate charge? What is the maximum charge on the capacitor? C times E. So we will call it QM. Maximum charge on the capacitor, QM, is equal to C times E. Okay, if you look at the circuit, at any instant, let's say that there is a current flowing through the resistance, which is I, and I is changing. And so is the charge on the capacitor changing. We're looking at the charging process. When T is 0, what's the charge on the capacitor? When you just switch on, what's the charge on the capacitor? It's 0. And as T progresses, the charge on the capacitor builds up. And so does the current flowing through the resistance. So at any point, if we say that the current through the resistance is I, and at that point the charge on the capacitor is Q, we can set up an EMF's equation. It's called the EMF's equation, Kirchhoff's second law. What will that equation look like? Will it look like this? E is equal to IR plus Q by C. Because you know that the potential drop across a resistance is I times R. And what's the potential drop across a capacitance? Q by C. So when you add those two together, you have to get the total voltage of the battery. That's the physics involved. Now it's math. So I hope you got the physics part of it. At any instant, the total voltage of the battery is equal to the potential drop across the resistance added with the potential drop across the capacitance. Now we know that we can substitute for I. I can be written as dq by dt, isn't it? So that becomes R dq by dt plus q by c. Now we can rearrange this. When you rearrange it, you get E minus q by c. Taking that to the left side is equal to R dq by dt. And again, CE is CE minus q divided by c. When you take the LCM on the left side, is R dq by dt. Right? When you take the lowest common multiple, C, multiplied with E, that will become CE minus Q by C. Does that make sense? Does this part make sense? CE minus Q by C is equal to R dQ by dt. We're trying to get an equation for Q as a function of time. We want to see how the charge builds up on the capacitor as a function of time. We want to see whether it's going to be linear, is it exponential, is it going to be quadratic. We're going to look at how charge builds up on the capacitor. That's what we're trying to do. So the next step would be CE minus Q is equal to, take that to the other side, becomes R times C dQ by dt. We're setting it in a way that we can integrate. So you pull the like terms together, you get dQ by C minus Q is dt by CR. I've pulled the like terms together. If you can see dQ and Q on one side, correct? So we are now ready to integrate, and you got dt by CR on the other side. So the limits on the left, 0 to Q of dQ by C minus Q is equal to integral on the right side, 0 to T of, did you get that? Yeah, I just put the integral on that side. Now, when you integrate, you know that integral 1 by x dx is natural log of x, isn't it? So that is supposed to be ln. It's not that clear, I'm sorry. So natural log CE minus Q, limit 0 to Q is equal to, the right-hand side, of course, is T by RC. Let me slow this down. And then Q first takes the value Q, and then Q takes the value 0. Isn't that how it is? So your first term will be negative natural log CE minus Q. What's your next term? Negative of negative, isn't it? It should be minus, minus. Okay, so it's going to be that minus, again minus, natural log CE, because Q takes value 0. That's equal to T by RC. And of course that becomes a positive. See, but what I'm doing here is I'm going to take that negative to the right side. So the signs on the left-hand side are reversed, as you will see. Minus T by RC. So I'm reversing the signs on the left-hand side. Because actually, natural log CE is supposed to be positive. And the first term is supposed to be negative, isn't it? So I just reversed the signs and took that negative to the other side. Now you of course know that log A minus log B can be written as log A divided by B. So that's the next step. So you can write that as natural log CE minus Q divided by CE is equal to minus T by RC. And then you also know the, okay, I just divided CE by CE to get 1. 1 minus Q by CE is minus T by RC. Now what is the opposite function of natural logarithm? Exponential, isn't it? Natural log is exponential. Did you know that? So in place of putting natural log on the left-hand side, can I put exponential on the right-hand side? Yes. That is the next step. So we just have 1 minus Q by CE on the left side is equal to e to the power negative T by RC on the right-hand side. And then look, we're looking for Q. We're trying to separate Q. So you just go ahead and get Q by CE is 1 minus T by RC, and therefore Q would be C times 1 minus exponential negative T by RC. And what is CE? Isn't it the maximum charge? You just told me before we started, the maximum charge, which we have written as Qm, is C times E. All right, in place of V, we are using E. Yeah. Okay, so the last and the final formula becomes Q is equal to Qm times 1 minus e raised to minus T by RC. Okay, so CE is equal to Qm, which is the maximum charge in the capacitor. And that becomes maximum charge is equal to Q is equal to Qm 1 minus e raised to negative t by RC. Okay, but if you put T is equal to RC in that equation, don't you think that RC and RC will get cancelled? You get e raised to negative 1, which is 1 by E. And from your calculator, if you take 1 by E, you get 1 by 2.718. Check it out on your calculator. 1 divided by 2.718 is going to be 0.368. And so 1 minus 0.368 is 0.632 QM. So if T is equal to RC, and that's called the time constant, T is equal to RC is called the time constant, we get the charge on the capacitor is 63.2% of the maximum charge. And that's a very important constant. The time constant of a CR circuit is very important. And how do you find the time constant? Just multiply the resistance with the capacitance. For example, if R is equal to 1 mega ohm and C is equal to 1 microfarad, what's the time constant? Come on now. T is equal to 1 mega ohm. What did I say? R is equal to 1 mega ohm. C is equal to 1 microfarad. What's T? 1 second. That means in 1 second, the charge is going to build up to 63.2% of its maximum charge. So you see that it's a quick process. Now let me ask you this. How much time will it take for it to get completely charged? How much time will any capacitor take? We're talking about an exponential charging. Do you notice that it's an exponential function? And what do you know about an exponential function? That it reaches a maximum only after infinite time. So that means, theoretically, a capacitor never gets completely charged. Well, of course, practically, it'll get almost to a maximum within no time, like 1 second, or 1.5, 2. So if you draw a graph showing charge on the y-axis and time on the x-axis, you're going to get an exponential graph that goes closer and closer to the maximum, as you can see, but doesn't touch it until after infinite time. And I'm trying to show where the time constant is. I'm trying to show that this point is almost where 0.63 of maximum is. If you watch closely, you can see that. It should be more than 50%, isn't it? 0.63, 63. So that is the time. Remember, this is the time axis. And so that is the time after which it reaches that charge. It's an exponential charging. Now, 0 is equal to IR plus Q by C. I, like I said, is dQ by dt, isn't it? So R dQ by dt plus Q by C. Get those RC together. Is that right? And rearrange to get dQ by Q on one side and minus dt by RC on the other side. Is that correct?
How do you get the Q on the bottom? Because if you divide by Q, when you have a Q in the second P2.
I just took Q to the other side, did it all in one step. Took the Q to the other side, it will become negative Q. One of the factors will become negative, right?
Yeah.
And then divide.
Yes.
And reverse. Just try. I just tried to cut down on the steps there, but you can write it down in 1 or 2 steps. Take it to the other side, try. You get it?
Yeah.
Okay. Now, the important thing is when you integrate, what are going to be your limits? What are your limits of integration? You have a fully charged capacitor, That is discharging. So,
Q to 0.
wait. It'll be Qm to Q. Because we do not know whether a capacitor would get completely discharged. Remember that when you charge it, it never completely gets charged. So we cannot say, all right, it's going to get fully discharged. So you cannot say Qm to 0. You have to say Qm to Q in a time 0 to t. So when you integrate, remember that, that's a major mistake that students make. Maximum charge to Q drops to Q in 0 to t. So integrate that. And when you integrate this, of course, it's natural log of Q, Qm to Q, and that is minus t by RC. Substitute the limits, you will get, first you have to put Q as Q and then Q as Qm. So when you get that, natural log Q by Qm is equal to minus t by RC. And then in place of the natural log, like before, you write it as exponential. And then you get your equation finally as Q is Qm e raised to minus t by RC. Did you notice the difference between the charging equation and the discharge? There is no 1 minus. And do be careful about that. Because if it's Q is equal to Qm times e negative t by RC, it's discharge. But if you have 1 minus, it's charging. And what would happen if you put t is equal to RC in this equation? T is equal to RC. It'll become e raised to negative 1 there, right? It'll become Qm times 1 by E. And 1 by E is 0.368. Same thing in the reverse direction now. So if T is RC, then Q is Qm E negative 1. That's equal to Qm by E, which is 0.36 Qm. And then if you draw the graph of the discharge with T on the X and Q on the Y, it's going to drop down from Qm. Well, of course, it should not cross the line, okay? It should not, this part, you know what I mean. It should not cross the line. It should start right from the graph, okay? And then, you're going to say that when T is equal to RC, the charge is going to drop to 36% of the maximum. So it should be below 50. 36% of the maximum. Sometimes it's good to draw a graph, a charging graph on this. And I've given the applications like I told you before. RC circuits are used in wiper motors, traffic lights to produce sawtooth waves, or any kind of timing circuit where you need something repeating after a certain time. That's where you use the RC circuit, because you know it's going to take a definite time to charge and then going to take a definite time to discharge. So it'll keep repeating at that definite interval, charging and discharge. You see, that's how traffic lights are operated. Okay, I actually wrote down the problem in a short form there. Find the time taken. Somebody's really tall. I think Professor Chu. Okay. Time taken to reach a charge of 1 microcoulomb in a capacitance of 1 microfarad when connected to a 2-volt battery. And this is done through a 1 mega ohm resistance. So write down the given quantities. R is 1 mega ohm. Capacitance is 1 microfarad. We'll leave them as it is. And you're talking about charging. Q is 1 microcoulomb. The maximum charge is C times E. First you find that. Multiply the capacitance with the voltage to get 2 microcoulombs. So that's going to be the maximum charge. And then the equation I'm going to rearrange to make T the subject because we have to find the time, isn't it? Before we substitute, make T the subject. Don't miss the negative here. There's a negative here. And I tried to get rid of the negative there. You know it can be done, isn't it? Because e raised to negative x is nothing but 1 by e raised to positive x. Isn't it? So that's why I changed the negative into a positive here. And put 1 by on the other side. Okay? Simple math. Those of you who have understood, just go on, finish it, get the answer while I wait for. So T by RC is natural log of that whole thing on the right side. And T is equal to RC multiplied by that factor. Plug in the numbers and calculate. What do you get? 169. Because this is 1 mega ohm. 1 microfarad is 10 to the minus 6, and you know they'll give you 1, isn't it? I just picked easy numbers. So that's going to be 1, and natural log 1 by 1 minus half. So it's 1 by half, which is natural log of 2. Because 1 by half is 2. Natural log of 2 is 0.6931 seconds. So in 0.6931 seconds, it'll build up to 1 microcoulomb. What's the time constant of this circuit? What's the time constant of the circuit? How do you find the time constant of a circuit? CR. T is equal to C times R. What's C times R? 1 second. So in 1 second, it'll build up to 69.3%. But if you want it to build up to 50%, it's going to take 0.6931 seconds. Let me say that again. Here the charge is building up to 50% of its maximum, isn't it? It took 0.6931 seconds. If you wanted it to build up to 69.31%, then it would need 1 second, which is the time constant. You never get it. So conversion of a galvanometer into an ammeter. Just 2 small topics. What you do is, that's the galvanometer of resistance G ohms, and you have a resistance, small resistance, S ohms in parallel with it. You send that current I amps, Ig flows through the galvanometer, and I minus Ig goes through the shunt. Well, if the total current is I, and Ig is the maximum safe current through the galvanometer, isn't it? Are you with me? Or lost? You have adjusted the value of S here. You have taken the value of S in such a way that only current Ig goes through the galvanometer. And the remaining current, what's the remaining current? If I is the current coming in, the remaining current is I minus Ig, and I minus Ig goes through S. So the galvanometer is protected because only Ig is going through it. And this setup is not a galvanometer anymore. Now it's called what? That's how you change this into. So when you have a multimeter, actually, when you change those switches, what you're doing, in a sense, is you're changing the shunt. By the by, S is called a shunt. A low resistance connected in parallel with any instrument is called SHUNT, a shunt. So when you hear that word shunt, you should know it's a low resistance in parallel. Can you tell me the potential difference between A and B? How do you find the potential difference between A and B? What's the formula for potential difference? I times R. So can we do IG times G? Or we can do I minus IG times. That's the end of the story. There you go. So the potential difference across A, B can be written in two ways. Either IG times G or I minus IG times S. Because in parallel the potential difference must be the same. Isn't it? Yeah. And now rearrange to make S the subject. And you get this formula IgG by I minus Ig. Very important formula there. Ig is 1 milliamp, which is 10 to the negative 3. G is 50 ohms. You have to measure up to 1 amp. That means I is 1. And that's the formula. Plug the numbers in. Get 10 to the negative 3 times 50 divided by 1 minus 10 to the negative 3, which is almost 1, isn't it? 0.999. So you just take it as approximately 50 times 10 to the negative 3. And 50 times 10 to the negative 3 is 0.05 ohms. So you see, that is the small resistance that you have to connect if you want to measure up to 1 ampere. What if you had to measure up to 2 amps? How much would you have to connect if you wanted to measure up to 2 amps? So here is the only change. It will be 2. Come on. So the denominator will become bigger, which means the resistance will become smaller, isn't it? So remember that. The higher the current to be measured, the smaller the value of the shunt.
Essentially, we're saying for it to read 1 amp.
If you wanted to measure a voltage using this galvanometer, how much could it measure? Before you converted it. What was the maximum current through it? 1 milliampere. What was its resistance? 50 ohms. So how much could it measure maximum? 1 milliampere multiplied by 50, which gives you 50 millivolts, which is not even, it's nothing. So how do you make it measure high voltages? So now we're talking about a conversion of a galvanometer into a voltmeter. How do you convert it into a voltmeter? Okay, the exact opposite of what you did before. Now you put a high resistance in series with it. Okay, the potential difference between A and B. Potential difference is current multiplied by total resistance, isn't it? Current is Ig through both because they are in series, and you multiply. That should be equal to the voltage. Rearrange. We're trying to make Rs the subject, isn't it? You don't know how much resistance you got to put. You're making this the subject. Rearrange to get V by Ig minus G. That's the formula. So what resistance must be put in series with a galvanometer of, I picked the same number, 50 ohms. That gives, again, full-scale deflection for 1 milliamps. Now the only thing you need is to convert it to measure up to how many volts, isn't it? 5 volt. So that's the formula. And you see how you get a big number, because 5 by 10 to the negative 3 is 5,000. 5,000 minus 50 becomes 4,950 ohms. You got to put that in series with it to make it measure up to 5 volts.